Good afternoon, everybody. I'm Giuseppe Carbone from University of Calabria. I'm welcoming you to this workshop number 1 on innovative mechatronic solutions and approaches. I'm also welcoming my colleague, Professor Massimo Callegari from Università Politecnica delle Marche, who will co-chair this workshop today. As you know, this workshop is in the frame of, is focused at mechatronics, and it's aiming at a quite challenging, wide and multidisciplinary field. And today we will have a quite rich planning of presentations, which are scheduled with 10 minutes for each speaker. At the end, we will have a round table. In particular, I would like to highlight that this workshop is one of the activities that has been planned within the Intelligent Mechatronic work group that has been established within RIM community. So here you can see a list of presentations and the speakers which will later on be introduced in this online streaming. So we will have 10 minutes each, so it's very important to speak at this schedule to keep all the activities on time. So 10 minutes each presenter, I strongly recommend you to keep this time. And at the end, we will have a round table in which you can set up some questions, and we will have time for some discussion, especially on the possibility of disseminating the outcomes, the presentations we are running today, also within dedicated special issues that can be organized within JOMAC or MDPI machines journals. So I really would like to give a warm welcome to all the speakers and leave the floor to Professor Callegari, who will chair the first half of this session. And later on, I will follow up chairing the second part of the presentation. Massimo, are you online?
Yes, thank you. Perfect. Do you hear me?
So I leave you I leave the floor to you, and you can say a few words of introduction, and then we go directly straight forward to the main presentations. Thank you very much.
Thank you, Giuseppe, for your introduction. No, I just will go to the first presentation, but before I will say that I will raise my hand when 9 minutes passed, so that the presenters can be aware that they have just 1 more minute to conclude their presentation. I propose that we leave all questions and answers at the end of the 10 presentations, so that we can also start in this way the roundtable. Therefore, the first presentation is by Giuseppe Carbone himself, and he will present a speech about entitled Examples of Mechatronic Designs at the DMEG, his department within the University of Calabria. Please, Giuseppe, it's up to you. Giuseppe, do you hear me? Giuseppe?
Can you hear me? Can you hear me?
Yes.
Okay, sorry about this. We are just switching from one presentation to the other. And yeah, you should be able now to see my screen. Can you confirm you see my screen?
Yes, we can see it.
Great. Okay. So in this brief presentation, I will just quickly introduce some examples of mechatronic designs that have been developed at the University of Calabria in Rende, Italy. So here is a picture of the main campus. The University of Calabria is located in the south of Italy, in the region Calabria. So here you can see the main staff members of the team regarding mechanics of machinery. So myself, Professor Gatti, and Professor Mundo, who are working on the topics related with mechatronics. In particular, Professor Gatti is mainly focused on nonlinear stiffness and design of robotic components. Professor Mundo is quite well focused on multi-material design, also of robotic systems. And myself, I'm focused at design of innovative devices and with a broad range of applications, in particular, for example, as related with rehabilitation. So as you know, mechatronics is a very wide field with a quite large number of applications and a very broad multidisciplinary background. So here I'm presenting just a couple of ideas and solutions that have been developed just to drive later on the discussion in the roundtable. So for instance, we have been designing Cube. We have patented this design of a cable-driven device which can be used for the rehabilitation of lower and upper limb at home. So the idea is to have a device which can be easily portable and placed in a home desk. So also we have developed a similar approach with a delta-like parallel architecture as shown here with the concept we named addutor. For this device, we have an international patent, and we also won the regional Smart Cup for establishing a spin-off company. So here, again, we also won the Best Paper Award at the Medical Robotics Week this year in Basel. Okay, this is quite user-friendly. We have been developing also a user interface and a set of sensors. This tells you how much we are in need of an integration of different expertises and knowledges, including, of course, mechanical design, but also sensors, also information technology, computer science, and so on and so forth. Also, we need medical feedback, we need ethical, we need to sort out ethical challenges and so on. Going to a completely different application, we have been also developing with a similar approach a 3D printed prototype for an horticulture application. Some technical problems. Okay, sorry about that. Problems with the computer. So the application was for harvesting of saffron flowers. This is commonly a handmade work, which is making a lot of pain for the workers, which need to stay down with their back, and this can be somehow they can get some relief by using a kind of gripper as proposed here. Again, in this case, it's a mechatronic solution which integrate mechanics and combine sensors, computer science. We need to program these devices. We need also to clear regulatory rules and to get user acceptance. So there are very common challenges which we are facing nowadays, and it's very important. We are prepared to keep a broad multidisciplinary approach, which is actually the basis for even the word itself. Mechatronics means combining different skills and their expertises. So I feel it's very important to stimulate collaborations and working teams rather than approaching a topic from a single background. As last slide, I would like to introduce our latest project, which is a collaboration with University of Belgorod in Russia. And there, the Ministry of Research of the Federal Russian government has funded an international laboratory based at University of Belgorod with 14 staff members under my coordination. And the main aim is to develop an innovative robotics, but I would say mechatronic device for aliquoting of biological materials in collaboration with the institute which is developing and producing the Sputnik anti-COVID vaccine. So with this, I would like to close my short presentation and introduction, just hoping to stimulate further collaboration with colleagues from a different background and expertise. We are in need. We are very open, and we are hoping to establish even more collaborations, as we feel really good achievements, proper innovation can be achieved only in a multidisciplinary team. Thank you very much for your kind attention. I give the word back to Professor Callegari for the next presentations. Thank you. Massimo, are you online? Can you hear me? Can you hear me? Massimo? Massimo has some troubles. Okay, I'll stop sharing. If Massimo has some troubles, meanwhile, I would like to call Matteo Palpacelli for the presentation of the next paper. Is Matteo there? Matteo Palpacelli, I can't see him. No, okay. Massimo, are you there? Massimo, are you there? Attendee? It's not there. Sorry, Massimo, can you hear me? Massimo, we lost connection.
Giuseppe, can you hear me?
Okay, yes, now I can hear you. So I give the word back to you, and I guess now it's the turn of Matteo.
Yeah,
we don't see him.
It's me, but I don't know if.
Fine.
Yes,
okay.
But I don't know how to share my screen.
Yeah, ok, deve condividere lo schermo. Promote to panelist. Okay, you should be able now to share your screen.
Okay, now I can see all the tools.
Great.
Okay.
Giuseppe, I'm here again.
Yes. Yeah.
So I'm trying to activate my video.
All right.
Trust camera.
Maybe I have to switch off mine to.
I don't know if you can see me. Yeah. Okay.
Okay, now we see you.
Yeah. I have to. Okay, none.
Sorry, in the meantime, Giuseppe, do you hear me again?
Okay.
Yes, we hear you and we see you. That's
okay. Okay, thank you. Now I'm up again. Sorry for the delay.
No problem.
Okay, I'm here. I'm trying to share my screen.
Anyway, we see you and we hear you all fine.
The tool. Okay, here and presentation. Okay.
Okay, now we see also your screen. Please go ahead.
Okay. So probably you see my screen.
Yes. We see
Okay. Okay. Thank you very much, Chairman. Anyone who knows me and also Professor Callegari and our research group knows that one of the major research topics that we have been following in the last 10 years or more is parallel robotics. And only recently we've started to investigate also collaborative robotics, and we have many initiatives in our region. And the first is a laboratory called iLab that is started probably it will start in the next month with its activities, and also in additive manufacturing with a laboratory here in Ancona. And nevertheless, we have recently formalized a collaboration with a company, and this company is interested in linear guides and also parallel kinematics machines, because they they want to produce parallel kinematic machines for the measurement sector. And so the collaboration give us this opportunity to study the mechanism that is the focus of this work. And so this is the overview of this work. You can see so I will talk about the context and the aim of the work, and I will introduce the design specifications of this machine, and some information about the kinematics and the optimization problem that allowed us to find the parameters, the geometrical parameters of this machine. And I will conclude my talk about the kinematic performance and the prototype of this machine. So Vacuum Fab is a company in the northern part of Italy, and the core business of this company is the manufacturing of linear guides, and you can see also a picture of the products that they produce. And in the last 2 years, they started to study also devices for the measurement sector, as I told you. And in particular, they are interested in machines that have high precision, and they will be used in the testing of microelectronic components, in the measurements in extreme environments, such as ultra high vacuums, and the name of the company is connected with this field of application. And so we have this collaboration, and we have so the company commissioned us to study a micro positioning device based on their linear guides. So here you can see the design specifications of the machine that they asked us to study. And as you can see, the overall dimension is quite small, is 350 to 125 millimeters, and a translation along a main direction of 125 millimeters, and the other two directions quite smaller. And a rotation angle of plus or minus 5 degrees in the 3 directions, and a repeatability in the translation of 1 micrometer plus or minus, and rotation repeatability of 2 by 10 to minus 4 degrees, and a payload of 1.5 kilograms. So starting from these design specifications, we studied the many architectures, and we found the hexaglide kinematics as the best solution to go in the direction of these specifications. And as you know, the hexaglide kinematics has 6 actuative parallel sliders. So this is the most common architecture. And as you can see, it has a main directional translation that is the one given by the sliders. and 6 rigid legs of constant length. One of the parameters that has to be optimized is the length of this architecture, and an hexagonal moving platform. There are many opportunities, but this one is the one that allows to have a connection, an easy connection of the legs with the platform, and also has a symmetrical disposition in the polar disposition of the points, and 12 spherical joints. So the kinematics of this machine is quite common and known in the literature, and so we formalize the position kinematics as others. So using the constraint of the legs that has to have a constant length, and starting from a parametrization based on Studi's parameters and homogeneous transformation, we studied the inverse and the direct position kinematics. And just a few words about these two problems. The first one needed to find a selection routine to choose among the two 6 theoretical solutions. And the other one is based on Newton-Raphson algorithms to find the solution among 40 theoretical ones. So after the first part of the study that was based on, as I told you, a known study about kinematics, we decided to study the differential kinematics that is typically used to find the performances, the kinematic and static performances of manipulators. And the form of the differential kinematics is the conventional. As you can see, there are a Jacobian matrix, the geometrical and the analytical geometric Jacobian matrices in this first form. And there is also a connection between the velocities at the joints, the actuation of the linear guide, the velocity. See, you can see a voice in the background. Okay, and so there is a connection between the velocities in the joints and the velocities in the Cartesian space. And we found also the singularities studying the geometrical form. With the screw theory, we have a geometrical form of these matrices, so it's quite easy to understand which are the conditions that bring singularities to the machine. And so we, of course, we tried to find a mechanical solution far away from these conditions. And we studied the problem with an optimization problem based on a partitioning of the Jacobian matrix. So the full Jacobian matrix is the one obtained with the inversion of the geometrical one with multiplied by the analytical. And so we divided the study between the rotations and the translations with these two matrices. And we defined the local and global indexes based on the condition numbers of the Jacobian matrices, and is given by the ratio between the eigenvalues of these two matrices. And after that, we defined also an objective function based on the global condition indexes found in the top line, in the upper line. And so here you also can decide which weight you want to give to the rotation and the translation with these two coefficients, k omega and kv, and their sum is 1, in order to have an objective function that has a range from 0 to 1, when 0 is the best solution and 1 is the worst. And many parameters are inside this function, and you can see the phi and r, that are the two parameters that I showed you before for the platform, the radius of the platform and the position of the points on the platform. L is the dimension of the leg, and the other 4 parameters are the distances in the lateral position of the stages at the fixed base. And also the pH is the the position of the platform in the home configuration. So we started our optimization with a routine based on the MATLAB symbol optimization toolbox.
Matteo, you only have a few time to finish your presentation. Okay.
Yeah. And so after this optimization, you can see the result is the last line where you can find the best values. Of course, with an average and more practical values. And after that, we studied also the performance of the manipulator, defining a stage for the linear guides provided by the manufacturer with the 15 nanometers resolution. And here you can see the home configuration with a white point and the performance on a vertical plane of the manipulator, and also some tetrahedron, force tetrahedron that shows the performance in terms of forces in the workspace. And just to conclude with this company, we had as you can see, we had also the opportunity to produce, to realize, to build a prototype, and this prototype has magnetic bolts for the connections of the legs with the platform, with two platforms, and it seems to have the performances that we, of course, in the first tests of this machine, has the performances that we found in our study with this theoretical study. Okay, that's all.
Thank you, Matteo. If you want, you can raise your questions at the end of the 10 presentations. So I will turn to next presenter, who is Riccardo Minto, I think. He's a PhD student at the University of Padova, and he will present a work developed together with Boschetti and Trevisani. And the title is Cable Robot Recovery Strategy in Case of Cable Failure. Please, Riccardo, it's up to you.
Good morning, good afternoon, and okay. Do you see my screen now?
Yes.
Okay. So, good afternoon. I'm Riccardo Minto, and I'm here to present you our work regarding cable robot recovery strategy, especially in case of cable failure, which we have carried out with Professor Boschetti and Professor Trevisani. So, starting with a short outline of the presentation, we will start with a short introduction to cable-driven power robots, focusing on cable failure and the need for recovery strategies. A short presentation of our recovery strategies that we have developed with our group, and the experimental setup that we have developed to test our recovery strategy. So, starting with cable-driven power robots. Cable-driven power robots offer our power robots whose links are composed by cables, and so they offer several advantages. First of all, as power robots, they provide for high payload capacity and high speeds of the end effector. But differently from the rigid link power robots, the design, which is, since their links are composed by bonded cables, it is possible to obtain a simple and cheap design and also carry out large workspace and manipulation tasks. However, there are some safety issues when working with cable robots, mainly cable failure. Indeed, as you can see in this video, when the a cable breaks and the skycam, in this case, falls down on one of the players, and indeed, cable failure have a sufficient frequency of accidents. For example, in 2013 and 2016, there were also some injuries due to skycam falling, and so there is a need for recovery strategy. And it is not as simple as with rigid manipulators, where it is possible to break the actuators to stop the end effector, since it could lead to other cable failure and worsening the problem. And also there is a need to ensure positive cable tension, especially when working with the cable suspended parallel robots. So where the positive tension in the static workspace is carried out by the gravity. And so we need for a recovery strategy that moves and stops the end effector in a safe pose in the static equilibrium workspace. And when our group started this work, the literature was mainly focused on the analysis of cable robot failure modes. So, for example, not only cable failure is the most important one, but we have also, for example, cable break, cable compression, or wire jamming. And the first solution that were proposed for cable failure were, for example, adding auxiliary cables, but this adds complexity to the system. And so other solution based on adding a compensation tension on the remaining cables were proposed, but it is possible only for overconstrained applications where the cable breakage do not change the static equilibrium workspace, that do not change the workspace of the cable robot. And so it is possible to add additive tension and stops the end effector. So we have developed a cable failure recovery strategy, a cable failure recovery strategy that moves the end effector inside the static equilibrium workspace, as you can see in this figure. And this recovery strategy is in two phases, with a first phase, which is called connecting path in our work, which breaks the velocity of the end effector in order to change the end effector velocity towards the desired safe point, and a linear trajectory which moves the end effector towards the safe point. To change the velocity direction, we need to impose a force, we need to apply a force that minimizes the components of the velocity which are orthogonal to the desired direction. And this force should also satisfy constraints on the maximum cable tension and on the maximum actuator curve, because the actuators should apply the required force. These constraints are also adopted in the linear trajectory, as you can see in this figure, where we have the acceleration constraints during the motion direction. And as you can see, the end effector acceleration is constrained along inside the limits indicated by the black lines. And therefore, the trajectory depends on the different starting point, failure point. And the recovery strategy was also tested in experimental devices, which we have constructed in our laboratory, in the automation robotics laboratory, and with an industrial PC, 4 B&R servo gear motors controlled by two back-off servo drives. To control the actuators, we adopted an hybrid control based on a inverse kinematics PID and an inverse dynamics feed-forward. The PID was needed to control the trajectory of the end effector during the not only during the recovery trajectory, but also during normal operation. However, we also needed to ensure that the cable tension was positive. We do not want compression on the cables. Therefore, we introduced the feed forward. And as you can see, we tested our recovery strategy in this example, where you can see the marked cable that is slack because we unwinded our cable to simulate the cable failure. And you can see the 2 steps of the recovery strategy. 2 steps that are also identified in the experimental results. You can see by the red line and the green line, represented the braking phase and the linear trajectory. And therefore, in conclusion, we have considered a cable failure for cable suspended parallel robots, which was not considered so much in the literature before when we started some years ago this work. And a 2-phase recovery strategy was defined and was tested in simulation. Okay, was tested in simulation and then was also tested with experimental application. That it is still tested, experimentally tested. Okay. So lastly, I'm going to share you some references to our work regarding our study on recovery strategy. Okay, can you hear me?
Yes, I can hear you.
Okay, I think there was some problems. Okay, and so I was.
I think that Chiara Cosenza has his microphone open.
Okay.
So please, thank you.
Thank you. And so to some references for our work during the years, and thank you for your attention.
Thank you, Riccardo. You've been just on time. So I propose that we go on with the other presenter just to stick to the schedule. Possible questions can be raised at the end of the presentations. So the next speaker is Antonio Frisoli. I think that Antonio will present the next paper.
No, it's Massimo Solazzi.
Okay, sorry. So it's up to you, Massimo. Your presentation is entitled Advanced Human-Robot Interfaces for Remote Robot Telepresence. Massimo and Antonio and the other co-authors are from the Scuola Superiore Sant'Anna of Pisa. And so please, you can start your presentation, Massimo. Massimiliano.
Thanks, Massimiliano. Yeah, thanks. So, okay, can you hear and see me? Well, see
yes,
the presentation.
yes, we can.
Okay, so thanks for the presentation. Yes, we are from Scuola Superiore Sant'Anna, and this is all the names of the group that is involved in the human-robot interaction area. It is led by Professor Antonio Frisoli, and now I am presenting our last advances in designing and developing robotic devices for teleoperation and telepresence. So just a really brief introduction, and so of course, just sorry about okay, a problem with my presentation. So sorry about that. Of course, so you already know the definition of teleoperation, where we have a master robotic devices or a control station that is used to remotely control a slave, what we call a slave robot, or in some cases also a virtual robotic avatar. And the applications can be the emergency after disaster scenarios, or operation in dangerous environment in general, or hostile environment. So when you don't want to send an operator or a human because it's dangerous, you can send a robot. Or the interaction with remote virtual environment, so controlling a virtual avatar. And while teleoperation is focused on controlling the robot, telepresence involves the highest immersivity of the operator. So there is the embodiment of the operator in the robotic avatar, in the slave remote robot. And of course, exoskeletons represent the robotic system where the highest physical symbiosis with the human is achieved. So, of course, they are the better robotic solutions for achieving the embodiment that is necessary for a telepresence system. And in particular, the full upper limb exoskeletons for bilateral operation, so the operation with force feedback, improves the control of remote robots. Why? Because they they can assure high dexterity and an intuitive control, because I can control the slave robot directly moving my hands, my arms, my torso, so my body. I have a localized force feedback directly in my limbs. So all these advantages lead to let the exoskeleton to be really suitable for complex bimanual tasks. So they are the best solution when I want to perform complex tasks during teleoperation. And for a robotic challenge that is going on, the name is an Avatar X Prize. We developed, of course, it is also the result of several researches in this field that we carried out during the years, also with other projects. So we are developing this system for telepresence, and it is made by a master, so a control station, and the slave robotic avatar. And in the control station we have, as I was saying, two arm exoskeleton, arm and end exoskeletons, to control the movement of the robotic arm of the slave, and also the gripper that are actually robotic hands, dexterous robotic hands, pedals for navigation, and a head-mounted display to have stereo camera streaming, so stereo visualization of the remote environment, and stereo headphones and microphones to also interact with the remote environment by audio. Sorry. And so this just is archive repertory video. It was just the first test and final robotic slave robotic arm. It was just to just a focus on a picture of of the roadmap for developing the system. So we started by just really simple scenarios that was not remote, of course. So we were just testing the control, and then we arrived to a final system. So this one, it is the picture actually of me in the control station. So with the full devices. So as you can see, I'm wearing the arm exoskeleton and hands. So the hands are under actuated, so they have all the degrees of freedom of my hands, so no restriction to my movement. And now I have the pedal. Now I'm not using with the feet, but in front of me there are the 3 pedals for the navigation, and the HMD display for the visualization. While this one, it is the mobile platform that we use as a slave robot. So the platform has a mechanical wheel, so omnidirectional wheel, depth cameras for navigation assistance. So it is not autonomous, but it is assisted navigation, just for safety. The stereo camera for the video feedback, anthropomorphic hands, and redundant arms with 7 joints like human arms. And this one, it is a demonstration, a video for the demonstration of the capabilities of the system. So in the small box, there's the remote environment, so with the operator in the exoskeleton that is controlling both the arm in a scenario that involves the the natural communication and interaction, no, with another human, with the other environment. So now you can see, maybe I skip, so that the device is able to grasp objects, receive the feedback, so can physically interact with the environment. So now he just cheers the glass, but he can also perform precise tasks. And on the left now you can see, of course, now it cannot be the stereo visualization, but the two images left and right that the operator receives to have the stereoscopy and such a way that he can perceive the depth in the environment, so he can perform physical tests, like for example pointing something. And now I want to just it is really long, time is finished, so just to skip. So this one, it is a close-up on the so same scene but on the control station. So you can see also the arm exoskeleton has 7 degrees of freedom, so full mobility and full actuation on the arm. The hands, the robotic hands, has a under-actuated kinematics with the total 17 degrees of freedom for the hands, but only 5 motors. So it is a high amount of under-actuation because of course the dimension for the arm, for the hand exoskeleton is critical. So we apply the force feedback in all the phalanges or the fingers, but with only 5 motors. These are an optimal solution to keep the system compact and light. While again, so this is the navigation capability. So with the 2 pedals, I can control all the 3 independently, all the 3 degrees of freedom that has the platform with the mechanical wheel on the floor. So also not only dexterity for the arm and hands, but also dexterity for the movement. And here you can
Massimiliano, you just have a short time to conclude your presentation.
Yes, this is the last video, last scene, so I just skip when there is some physical interaction. And so this is a close-up of the system with the arm, hand exoskeleton and arm exoskeleton. So you see, all the design is made in our lab, and okay, that's it. So if I just shut down the video and the presentation. So many thanks for your attention, and if you have any questions, I'm here.
The questions in the end. Thank you, Massimiliano. So I think we can turn to the 5th presentation, which is given by, I think, by Lorenzo Agostini. Is it right? From University of Bologna. Or is there anybody from the University of Bologna delivering the presentation?
I'm here. I'm Lorenzo Agostini.
Okay, fine. So you can introduce your co-authors. I just only say the title of your presentation, which is Safety in Robot Arm Guidance. So please introduce the other co-authors in your presentation. You can go on.
Yes, setting up the presentation. Give a second, because I'm here in Rome.
Yes, no problem. Take your time. So in the meantime, I can mention the other co-authors who are Monari, Palazzi, Avallone, Chen, and Rocco Vertechi.
Okay, so sorry for the delay. So hello everyone, I'm Lorenzo Agostini, and today I will present a ready introductory work about the safety in robot arm and guidance. So we have always been used to think about the robot for industrial application or assembly that are physically separated from the workspace of the operator. But now with the collaborative robots, the operator and the robot can share this workspace. And there can be different forms of this human-robot collaboration. They can coexist, so stay in the same place, but with a different workspace, or they can have a sequential collaboration that can cooperate, so sharing the workspace and doing sequential collaboration or together to assembly like something. And but the most for sure the most complicated one and the most complete, let's say, is the responsive collaboration. So in this kind of collaboration, the robot and several issues must be addressed in order to be to have a responsive and safe collaboration among these two actors that are the robot and the human. So for instance, a mechanical interface must be designed properly for the cooperative work. The robot must have an advanced control in order to answer to the feedback of the human. Sensor disposition must be designed and think about it, because in order to monitor it, monitoring the safety interaction, and the sensor can be placed on the workspace or on the robot or on the humans. And then there can be a different kind of event that can be also dangerous for the human or for the robot. Like for instance, a collision, so unwanted collision that can be injure also the operator. And another last point, it can be also the ergonomics of the posture of the operator working with the robot. So all these things must be addressed when we imply this responsive collaboration. So here in University of Bologna at Sinolab, where we have done, me and my group, we have done a research project that is funded from nationally from INAIL and a European project funded from COVR with the topic of being safe around collaborative and versatile robots in shared space. And with this objective, we have covered all the issues that I mentioned in the previous slides, with focusing on activities that involves the use of powered end tool, for instance, a driller. And we have listed like 6 main points in order to guarantee the safety around robot arm and guidance. For instance, a protocol testing framework. We have think about also the monitoring sensor, which kind of monitoring sensor and where to set this kind of hardware in order to monitor the safety of the collaboration. And also we think about the robot control strategy in order to assure this safety interaction. Safe interaction. Then also we have work on the effects on the collision that the robot can have on the human body. So we have set up a framework where we could simulate the impact between the robot and the human. We have done also the simulation of the ergonomics of the human while he's working with the robot. And finally, we have also implemented an app in order to compute the repetitiveness index while the work is working with the robot, in order to calculate if it's doing an heavy load that so it needs a break or not. For doing this, we have an hardware equipment in our lab that is composed by a 7 degree of freedom hand-guided cobot arm from Farncanica that is very precise and have a payload up to 3 kilos. Then we also equipped the end effector of this robot with a 6-axis force torque sensor from Schunk that has a very wide measurement range with compact design and high resolution. And for as monitoring sensor, we have we are using a HIMU suite for in order to track and reconstruct the body motion of the worker. So this kind of suite is this kind of suite is composed by 17 IMU units. That an IMU is a unit composed by mainly 3 sensors, 3-axis sensor that are the accelerometer, the gyroscope, and the magnetometer. And then we use a drilling tool in order to simulate the working condition. So all these points we have elaborated these points in parallel from our group. So we developed this kind of testing protocols, test bench in order to measure and to understand which kind of mechanical interface is needed in order to have a right collaboration between the human and the robot. Then we have implemented a calibration procedure in order to understand the posture of the worker while he's working with the robot. And so for doing this, this kind of monitoring, we needed this kind of calibration because the IMU sensor can be affected from the electromagnetic interference. And then we have also worked on the collaborative robot control. So computing 4 kind of different controller for the gravity compensation and the friction compensation, and the controller of the robot in order to assess, to help the worker while he's doing the task as the drilling of a hole. And then we have also, like with all this kind of hardware, we've implemented the system integration. So in order to make to implement the communication between the sensors and the robot in order to assure always a safe interaction and a safe disposition of the robot with respect to the human. And then we have done a set of activities in order to study and to simulate the effects of a bad, let's say, collaboration between the robot and the human. So we have done a simulation analysis on ANSYS LSI Dyna for the implementation of the impact effect of the robot on a arm of a person. And we study all the protocols and the safety requirements in order to understand how much the robot can go without hurting the worker. And we studied also still in a simulation framework the ergonomics of the worker while he's doing the task with the robot. So we use an any-body system, and we understand without multiple sensor the kind of effort of the muscles of the worker. And finally, we have done this SARA app that can be used from production plan that use the collaboration between human and robots in order to understand if the human is in bad ergonomics position while he's using the robot. So in the end, we addressed all the tasks that and the issues that the human-robot interaction can imply when we have direct interaction between the human and the robot for a task, a common task. And we still are now trying to understand how to take out from the laboratory this technology and implement in real industrial plants. So thank you for your attention. We are Simon Lab of Laboratory of Bologna, and for any questions, I'm available. Thank you.
Thank you. Thank you, Lorenzo. You have been right on time. So now I leave the floor to Giuseppe, who will chair the remaining part of the session.
Thank you very much. So we switch physical chairs, and we go to the next speaker, which will be Mr. Spini.
Exactly. Yes, I'm here. Can you hear me?
Andrea Spini is going to present an overview of an innovative family of driving simulators. He comes from the University of Pavia. So let's share his screen, and then you can directly start. And just remember to stick at the 10 minutes time slot.
Can you see the presentation?
Just a few seconds to share.
Yes, we can see and hear you.
Okay, perfect.
All right, the floor is yours. Please go ahead.
Thank you so much. So, good afternoon to everyone. I'm Andrea Spini, and I'm here to give an overview of innovative driving simulators. Thus, the main topic of this presentation is driving simulation, and in general, simulation is defined as an imitation of something real, and it is related to the complex human perception system. First of all, driving simulator can be used in different fields, from entertainment to research, and also for advanced training. And a first classification can be based on the quality of the simulation produced, from the low-level simulator that usually in the driver seat in a car seat, which is fixed to the ground, and also the screen is fixed too. We can have the mid-level simulator that consists usually of a car which is accelerating in 1 degree of freedom. Instead, the high-level simulators are usually characterized by at least 6 degrees of freedom. Why at least, it will be explained later. And specifically, a driving simulator is a particular mechatronic solution that has the aim to replicate the vehicle dynamics and the induced feeling on the driver. And in this video, it's possible to see an example of the vehicle dynamics transformed in the robot dynamics for the purpose that I previously mentioned. Nowadays, driving simulation is used for different purposes and different applications. And the one that goes from the driver, like we can see here, the analysis of the driver behavior, the analysis of the driver responsive, the effect of noise and vibration on the driver, and also the training in critical condition. We can also find the development of different tools and also the testing for these tools, like the human machine interface, the testing of the ADAS system, and also the control system design, like system in the loop and hardware in the loop. And finally, they can be used also for the tire and car development. And at this point, it is clear that a driving simulator is a useful mechatronic system, not only for entertainment, but also for research and development. Given an overview of driving simulation field, here the main components of a driving simulator are introduced. Firstly, as the driving simulation aims to reproduce the dynamic behavior of a vehicle and the feeling on the driver, the main component is the motion system. And the dynamic simulator history and the study conducted over the years lead to this knowledge that a high-quality simulator needs 6 degrees of freedom. And it is right that the main part of the motion of a simulator is the motion system, but it's clear and easy to understand that if a particular motion is not linked to a correct view, the final sensation on the driver will not be realistic. And obviously, another component, another important component is the driver's cabin, important for the driver immersion in a high-defined environment. And as for the viewing system, the sound system play an important role for the final accuracy of the simulation and the driver's feeling. And we cannot forget about the auxiliary system like pedals, steering wheels, and seatbelts. And the final ingredient of a driving simulator is a real-time computer where all these components that we saw in this slide are taken into account. In this real-time computer, we can manage the sound and the view of the pilot, at the same time with the direct and then the inverse dynamic and kinematic analysis of the robot. So this is the typical setup of a high-level simulator, and this kind of simulator usually have some problems like the noise, the vertical encumbrance, the footprint, and the difficulty in having large movement and therefore maintaining acceleration for a long time. So due to these drawbacks, innovative solutions are required. And here comes into play the new family of driving simulator that I'm here to introduce. And this simulator that we can see in the video and the images, it's a unique driving simulator. It has been developed by a spin-off of the University of Pavia and in close cooperation with the university. And the innovative of driving simulator that we are seeing here is based on a decoupling and redundant degrees of freedom. Specifically, the simulator that we are looking at, it's 9 degrees of freedom. And the upper stage is made of is a parallel kinematic manipulator with 6 degrees of freedom. And the lower one is a cable-driven parallel robot. Specifically, we can see here the parallel kinematic manipulator as the upper stage. The lower stage is a cable-driven parallel robot. And it is worth to mention also the RIM suspension system at the lower stage and also the inertial compensation system. Let's see then this particular solution. Specifically, as I said, the motion system of this simulator is based on this structure that we can see on the left of this slide. And we have the 6 degrees of freedom parallel kinematic manipulator, the inertial compensation system, and the lower stage is a unique solution, a cable-driven parallel robot with 3 degrees of freedom. Usually for the lower stage, a Cartesian ray is used. And going in depth, the upper stage is responsible for the high frequency dynamics. Instead, the lower stage, the cable-driven parallel robot, is responsible for the lower frequency dynamics. And this solution of these two platforms linked together with 3 redundant degrees of freedom offer the possibility to extend the simulator frequency range, and it gave the possibility to change the yaw axis. The solution involved at the lower stage, as I said before, is unique, and it gave the possibility for a large workspace and for realize a sharp and compact system. And also, it offered the possibility to avoid shortcomings of traditional machine, like the Cartesian ray and slides that are noisy. Other 2 important characteristics of the motion system that I introduced before are the RIM lower suspension system and the inertial compensation system. The RIM solution, that is the one that we can see here, allow the simulator to move on the base plane, minimizing the friction and deleting the phenomena like the slipstick. However, the runner block can provide a binding reaction force only upwards. And in order to prevent the detachment of the pad, the sliding from the sliding surface, it is necessary to provide a force that counteract this. And this is performed with this electromagnet. The counterpart of using RIM solution like this one with a cable-driven parallel robot is the necessity of an inertial compensation system, and here it is. This inertial compensation system is a system of masses which, when accelerated, can create a force capable of compensating from the imbalance of the machine above. Here we can see the inertial compensation system from the top. And this system is also useful for introducing particular dynamics, which without this system would not be able to introduce. But not only components are important for this complex system, also the design phase. And I'm referring specifically to the sizing process. And the sizing process is based on the definition of force and torques on the structure and on the actuation system by a given platform trajectory. But for complex system like the one that we are speaking about, it's complex to define a predefined task to use for the sizing process, because since we are speaking about driving simulation, it depends on a lot of factors like the track, the driver, the car that we are using in the simulation, and also the weather. So it is clear that it depends on a lot of factors. And here's coming into play a statistical approach like the Monte Carlo method, from which a number of stories are generated. And with the integration of the motion QE algorithm that is responsible for the transformation of the vehicle dynamics in the platform dynamics, the most demanding task is extracted, and the sizing process can be resumed. And at this point, if it's necessary, an optimization step can occur. So as I said at the beginning, a fundamental role is played by the real-time system, and the main goal of this system is to not introduce delay in the control and the management of the simulator. And this real system is responsible for the communication between the different worlds that interact in this mechatronic application, and it is implemented via fieldbus. And with real-time, I refer also to the real-time controller that allow to the simulator to be controlled. Here, the dynamics and the kinematic analysis are performed real time in order to have all the information required for the control. And of course, as I said before, the vehicle dynamics has to be linked to the correct view and the correct sound for having the most realistic solution simulation. At this point, I've reached the end of my presentation. On the right, it is possible to see some steps of the overall project. Briefly, I summarize what I introduced in this presentation. We saw an innovative family of driving simulator based on the cable-driven parallel robot at the lower stage, with the motion system, with the inertia compensation system and the RIM lower suspension. We saw also a specific design tool for the sizing process, and we saw the necessity of a real-time system for this complex mechatronic solution. I came to the end of my presentation. I thank you for the attention.
Thank you very much, Andrea, for your very interesting presentation. Now we go to the next speaker, who is again from University of Pavia, and is Federico Insero.
Can you hear me?
Yes.
I will share my screen.
You see just a light blue screen.
Yeah, the camera is not working.
We see something coming on. All right, we see your screen and we hear you. So your presentation is regarding the interaction in human-robot collaborative tasks through brain-computer interface. So authors are Carnevale, Dmitriev, Giberti, and Insero. The floor is yours.
Thank you so much. So I'm Federico Insero, and I'm here for presenting this work called Interaction in Human-Robot Collaborative Tasks through Brain-Computer Interface. The aim of this work is to try to improving the collaborative robotics working on the kind of interaction. So in this case, we have used brain-computer interface as a kind of interaction in order to modify and alter the collaborative tasks. In this presentation, I show a brief recap about the features of collaborative robotics. I will show you the different kind of collaborative strategies that can be applied in collaborative robotics, together with the kind of interactions and technologies for interacting with robots. In the end, I will present our collaborative assembly task as an example for proving how the brain-computer interface can be used together with the collaborative robots. And in the end, I will draw the conclusions about this work. Briefly, The collaborative robotics, the collaborative robots are designed in order to be safe. So they are able to work together with the humans without injuring them. So they can work together in the same workspace. And also, due to that, they are able to reduce the amount of hard work and the repetitive task that the operator are subject to. So the robot can can effort the hard work that the operator should do during their job. And in the end, the efforts of this last year lead to an easy programming of cobots, because we need that the cobots are able to be reprogrammed during their life and during their work. Otherwise, for companies, could be difficult to reuse them as a tool. But we are focusing on a feature that is contained in the name itself. So the collaborative features. We need that the robot is able to interact with the human and collaborate with them. So we need the two ingredients to this. Mainly, we need that design, a good design and a good collaborative strategy of the robotic task. And we need a way for communicate with the robot. So we need technology able to interact. The different kind of collaborative strategies that can be adopted with collaborative robots are mainly four and known in literature, like the independent one, where we have the cobots that can work safely with the operator. But the operator and the robot are doing different tasks and working on different work pieces. We have the simultaneous one. We have an improvement in this case, where the operator, the robot are working always with different processes, but now they are working with the same work pieces. The sequential the sequential collaborative strategy have as main dependency the time. So the cobot and the operator are working always on different processes, but each processes are synchronized in this case, and they are working on the same work piece. But we want to use the supportive collaborative strategy, because we would like that the cobot and the operator are working together in the same workplace, on the same workpiece, on the same workspace, and working together for reaching the same process. So in order to do that in industry, we need that sometimes the robots are doing the most repetitive task and the supportive collaborative strategy. So we reached an hybrid compromise between the two collaborative strategy, and we arrived to the collaboration on demand. This collaboration on demand it's a mixture between the collaboration strategies independent, where the operator and the robot are doing different processes, and after an interaction that in our case we exploited, we have reached using the brain-computer interface, we can interact with the robot and pass to the real collaboration, so the supportive collaborative strategy. In order to interact, we can work on, we can study the different kind of interaction. The kind of interaction works and needs two components: the communication strategy, so the kind of messages that we need to share between the human and the robot, and the user interface, so the kind of technology that the operator should use in order to communicate with the robot. We are using them every day. For example, the first one is the teaching pendant controller that provide a joystick and a graphical interface for the operator. But we have also gesture recognition, the voice recognition. So we are using voice and gesture in order to control the robot. We have also haptic control in order to guide the robot. But we are focusing on the brain-computer interface, where the human can use its own brain to send command towards the robot, and without using hand or its voice. In particular, we have used the SVEP technique. Using the visual stimuli, we can excite the visual cortex area and get signals from the brain and send the command towards the robot. This kind of signal can be interpreted as a frequency recognition system. So the framework for which is working, in which is working this kind of system, can work in this way. So we have the human operator, which is using, for example, a brain-computer interface with an helmet with electrodes, and we have also the acquisition system of the data. Using this SVEP technique with visual stimuli, we can process these EEG signals and send command messages. These command messages should be mapped in the task of the robot. So after having chosen the right collaborative strategies and interact with the robot. In our assembly task, we have used together with a load cell, with a force sensor, in order to integrate an hand guiding control as a sort of haptic interface. This kind of control is able to send a guiding message to the robot, and so sending the trajectory to the robot, and the operator is able to use the hand to guide the robot. With this technique, the force control is able to sustain high weight, and so the operator should not keep into account the weight of the pieces that is mounting. In this video, I would like to show how we have used the brain-computer interface for switching the different kind of collaborative strategy. Here we are in an independent case. The operator now is looking to the monitor, and through BCI, we can send commands to the robot to enable the haptic control. Now, with the brain-computer interface, the operator was able to stop the haptic control, and the robot was able to fix the position of the bar. When the operator needs, can unlock this mode, look into the flickering screen, and it is able to return to independent collaborative strategy. And the operator is still able to mount and doing its process, and the robot itself is able to doing its own task. Now we are still returning in the collaborative mode, so in the supporting collaborative strategy, and we are still switching using the BCI. I would like to conclude that with this kind of collaborative strategy, so the collaboration demand, the robot was able to assist the operator effectively, so in an easier way and more simple, without previous knowledge of how to program a robot. We have exploited the brain-computer device in order to drive the robotic task using the SVEP frequency recognition. I would like to remark that for the SVEP technique, only 2 sensors are used, the 2 electrodes on the visual cortex area. So we don't need to use a very complex system to integrate this kind of interface. We have exploited in the brain-computer interface successfully with the haptic control, so with another kind of interface, and can be used with other kind of interfaces in a multimodal manner. This kind of framework can be used for any kind of other collaborative tasks, and so it's so general and can be used for every industrial case. Thank you for the kind attention. If there are some questions, please ask at the end of the workshop.
Thank you very much, Federico, for your quite interesting presentation and topic of research. Now let's move to the next speaker, who is Chiara Cosenza from University Federico II on Naples. Chiara, are you online?
Sì, sono online.
Great.
I'm here.
Okay, we hear you for your
I'm sharing
screen. Meanwhile, the topic of your presentation is tendon-driven mechatronic hands. So
yes, thank you, Giuseppe.
now the floor is yours. Please go ahead.
Okay, good afternoon, everybody. My name is Chiara Cosenza. I'm a postdoc researcher at the Department of Industrial Engineering of University of Naples Federico II. My research group is composed by Professor Vincenzo Niola and Professor Sergio Savino. Today, I will show you one research field that we are developing in our department, that is the development of a tendon-driven mechatronic hand. This is the outline of my presentation. I will show you the design concept at the base of this mechatronic hand and the state of art of the research activities that we are studying in this field. Then I will show you 2 applications experimental application, one aimed to the experimental measurement of the grip force of this end, and one is the application of vision system for the experimental characterization of the components of this end. Design concept of our end, as you can see, the end presents a differential mechanism composed by pulleys. Thanks to this differential mechanism, the force can be distributed among the different fingers composing this end. This end is a 5-finger end, and every finger is composed by 3 parts, 3 phalanges, the distal, the middle, and the proximal phalanges. The end tries to imitate the human end. This is a tendon activated system in which we have 2 tendons, a traction and an antagonist tendon, that are able to allow the finger closing and reopening. Current prototype that we are using, the whole movement of the end is activated by just 1 motor. So this is a strongly underactivated mechanism. As an alternative to electromyography sensor, we are using a force resistance sensor that thanks to a proportional control to the muscle contraction can guide the end to open and close proportionally to the muscle contraction. We used to use in the research activities about this end, we used to use before prototyping multi-body modeling that are able to study the kinematics and the dynamics of the end in silico. We have focused in the past our attention of gripping of this end, because we know that if you want to use this end as a prosthetic device, the grasping and the gripping abilities play a crucial role in this application. We have also focused our attention to the improvement of the control system and the activation speed. As you can see from the videos in the bottom part of this slide, this end is able to perform dealing activities such grab a bottle of glass, or since the high activation speed is able to even grab a flying object like a ball. One of the main important feature of this end is that is a low-cost prototype. The whole prototype device costs less than $100. We are currently improving this end to develop a thumb with a design with the anthropomorphic features like the human end, the human thumb. We are currently redesigning the force distribution and the palm design, even thanks to the employment of the multi-body simulation modeling. And we are currently testing a new sensor like a conductive rubber of different shapes to control the as an experimental activities that we have, that I want to show you, this is in this slide you can see the experimental evaluation of the grip force that we have performed thanks to the use of cylindrical handlebar embedded the single axis lead cell. This device is even 3D printed and assembled by us. And we have measured for this end and a mean grip force of around 9 Newton. Another application from an experimental point of view for the characterization of finger kinematics with the quantitative approach is the employment of vision system devices to experimentally measure the finger kinematics. This can be a good choice, the use of system for experimental characterization of this low mass component, because we don't have to use further sensors to measure the systems that are under activity. In this slide, you can see that we have applied digital image correlation between this information, this data, vision data, but we have already development this part even using a low-cost vision system like Kinect, Microsoft, or Intel Sense devices. So thank you for your attention, and I want to thank the organizer of this workshop to invite me. If you are interested, you can see at this website other more videos regarding the application of this end as a prosthetic devices.
Thank you very much, Chiara, for your nice presentation. And now we move to the next speaker, which is Perla Maiolino, who is going to present how to emulate bio-inspired and reconfigurable mechanisms.
Thank you so much. Okay, I'm going to
share your screen.
Yes. Okay.
Okay, we see your screen and we.
Can you see the presentation?
Yes.
Is it not in presenter mode, right? It's in the right mode. Okay, thank you so much for the introduction. I'm Perla Maiolino. I'm currently at the Oxford Robotics Institute, but I'm collaborating with Professor Zoppi at the University of Genova. So today I'm going to give you a very high-level presentation of what's going on in relation to bio-inspired and reconfigurable mechanisms and the work we are doing in both the lab. I mean, as already mentioned many times, we are looking to move robots from the well-defined task and constraint environment of manufacturing to have them sharing our space and interacting safely with us. And this require, of course, to equip them with new capabilities, and mainly these refer to provide them with highly adaptability, flexibility, safe human-robot interaction, but also high behavior diversity. So in this respect, we are interested in looking at insight from biological organisms that, of course, exploit their soft structure to be able to cope with a very harsh and difficult environment. As you can see here in a video of the octopus that is able to escape for its cage in a very flexible and smart manner. So this is the reason why my research in particular is devoted to soft robotics, and soft robotics is the field that aims to equip robots with new capabilities that are based not just on the control system, but also in material properties and mechanical intelligence and morphology of their body. So, of course, soft robotics is a new field that require to cope with new technological challenges, in particular in terms of fabrication. sensing, actuation, but also from the point of view of designing intelligent mechanical systems that can show passive behaviors can be exploited in intelligent manner. And of course, this is also, so we need also to face new challenges that are related to the control of this system, because of course, we need to find new ways to model the behavior, because they are compliant, so they can deform in theoretically infinite way. And for this reason, to precise control them, we need to equip them with the new sensing technologies. Also, we can exploit their adaptability, but on the other side, we need to implement mechanisms for change their stiffness. And since they are made by a soft compliant material, we need also to find a new way to guarantee their durability. And so looking at, for example, new material that allows self-healing. And finally, we are also interested in looking at new methods for computing on board on the robot instead to rely on rigid electronics. So in this respect, I mean, my research started to look at exploit this kind of soft robot in like for grippers. In particular, we started to look at modeling soft pneumatic actuator. This is a bellow actuator, and of course we are looking to theoretical model to like achieve the required bending of these systems and force. We perform finite element simulation and also experimental characterization to be able to get system that can grasp and manipulate soft objects, as you can see here. This system mainly are used in the context, for example, of agri-food robotics for harvesting and manipulation of produces, and they can, for example, show very high adaptability to different kind of objects. So this is a the first step that we start with this soft system, and but we also are so because to model the kinematic of the system is very difficult. We mainly rely on piecewise constant curvature approximation or variable curvature approximation. We also are interested in ways to be able to model the system kinematically in a more precise way, but at the same time be able to exploit some compliance. And so we started to look at origami structure, and of course here you can see that origami usually are made by like by folding a piece of paper, but we started to look at thick panel origami, and moving from paper folding to systems that are 3D printed, you can replace the spherical linkages in the zero thickness origami to spatial linkages in the thick panel one. And here we design a gripper that can be 3D printed in one batch, and that is made by the assembly of water bomb thick panel origami, 4 element of water bomb panel origami. And thanks to that, we can achieve a gripper with just 1 degree of freedoms that can be actuated, that can be printed in one batch, and can be actuated by using tendons. And here you can see, I mean, that's in this way we can kinematically model it very precisely, but we can also exploit in some cases the flexibility of the hinges to adapt to objects with different shapes. We are also looking to, and this is something that is going on at the moment, working to modular soft arm. So taking inspiration from the elephant trunk. And so looking at, again, system that can be 3D printed, we moved from the usual casting, silicon casting manufacturing with like towards a 3D printing system to have system more reliable and repeatable in general, and to simplify the manufacturing of this system. Here we are looking at building a modular robot that show greater flexibility and as you can see here in the video, and can cope with a very difficult environment, because you can control them to reach places that would be difficult for a rigid robot. Furthermore, as I said before, we were looking at integrating some soft sensing to this system, because we need to provide both exteroceptive and proprioceptive capability to this system. And we started to look at the design, modeling and design soft tactile sensing. This is a soft pressure sensor. It is made by a chamber, and is also actuated, so we can control the pressure inside the chamber. And this gives us the capability to tune the sensing performance, and so its static range, depending on the kind of range of forces we're interested to measure. So we can make this soft sensor stiffer or more compliant, and so change its measurement range. And so we are able to cope with different type of contact and forces in our task. Of course, we perform both a theoretical model, but also we look at how different kind of material could change the performance of the system. And we also tested, as you can see, like with different kind of objects, so changing the internal pressure, we can measure with a pressure sensor a pressure that is measured from this pressure sensor, actually. Yeah, sorry. Can I go on?
Yes, just please come to the conclusions.
Okay, sorry. This is I finish here. This is the last topic. And here, of course, we integrated these sensors on a soft end. Also, this end is pneumatically actuated and completely 3D printed. And we provided it with a compliant palm and also tactile sensors distributed on the surface. We perform the fingers are actuated with negative pressures. So there are some chambers here that are connected to and are actuated by negative pressure. And of course, here you can see that we design it to be able to have a dexterous end. So looking also at some benchmark as the fixed taxonomy to check that we could be able to reach different type of posture and manipulate different type of objects. We of course perform different experimental characterization of the end from the point of view of the range of motion and the force that we could that the end could withstand. And of course, I mean, this is a system that is completely 3D printed, and as you can see here in this slide, able to like grasp and adapt to different objects very easily. And this is the response of the sensor when the hand is in contact.
Sorry to interrupt you. Unfortunately, we have a very tight schedule. Maybe we can, if you can go to the conclusions, and then maybe you can get some time after questions.
That's it. It's okay. Thank you so much.
Thank you so much for your very rich and wide presentation on a very interesting topic. Let's come to the last speaker, who is in presence here. So I just move, and the presentation is on robot dynamics considering temperature effects. The speaker is coming from the University of Brescia. Please, the floor. Okay. Thank you. Hello to everyone. I'm Roberto Pagani, and in this presentation, I'm going to talk about a work related to the robot dynamics considering temperature effects. The other authors are Manuel Beschi and Giovanni Legnani from University of Brescia. The research activity started from the collaboration with a Chinese company, the Effort Intelligent Equipment, located not too far from the city of Shanghai. And recently, the company Effort chose our country to expand its potential by starting a collaboration with our university and by acquiring some Italian companies such as CMA Robotics for printing machine, Robotics motion control for the control system, of course, and the evolution in performing robotics for the assembly of the robotic cells. But let's talk about the research. This project focuses on the study and estimation of the dynamic parameters of a general mechanical system. And in particular, the main goal is to model the friction effects. Because why friction effects? Because it creates many problems related to motion control, such as trajectory tracking error or dynamic instabilities in general. So the issue researchers aim to solve is to define natural and easy to use experimental procedure to estimate the dynamics parameter of the robots and to add a new friction model, considering of course the joint temperature, into the complete dynamic model of an industrial robots. The dynamic model is based on the well-known equation that you can see in this slide, where the torque applied to the robot joints can be calculated knowing the inertial matrix, the matrix containing the centrifugal and collinear terms, the gravitational term, the friction effect, and the contribution of the external forces if there are any. Regarding the friction torque, some studies show that it can be modeled with good approximation by a polynomial function that you can see in this slide on the top. And it should be noted that this equation allows to model the relationship between velocity and friction torque only. So it does not take into account the variation in torque due to the temperature. As is known, in fact, friction produces heat that increase the temperature of a mechanical transmission, making the oil less viscous and progressively reducing the friction torque. The figure that you can see here shows the variation of the friction torque as function of velocity. Each curve was obtained at different temperatures. So after this finding, we decided to study the robot dynamic model considering the thermal effect. To analyze the behavior of the robot during the heating, we developed a ROS industrial driver to allow the complete automation of the process of sending trajectories and data collection. A well-designed test trajectory has to excite the influence of all the model's parameters, and to identify the dependency of the friction on temperature, the test has to be repeated during the time, and it is alternated with special high-speed trajectory to warm up the joint. So the procedure is start from the cold robot. The test trajectory is performed. The robot starts to warm up, and the data is to be collected. And this procedure is then repeated until the robot reaches its warm state. To better identify friction and inertial parameters, the trajectory are divided into three stages. The first one is optimized for the inertial parameter estimation only. The second is specially designed for friction estimation, and the third is the warming trajectory to warm up the robot. It should be noted that the friction identification is performed only one joint at each time to simplify its analysis. And the merge of all the trajectory sections, so inertial, friction, and warming generates one cycle, which has a duration of more or less 5 minutes. And to acquire enough data for the analysis of the model, we performed 24 cycles, which correspond to about 2 hours of experiment. The temperature of the gearbox is not available in most of the industrial robots, and this could be a problem, but we can estimate both the temperature and the thermal model from experimental data, and the estimation is possible considering different value of joint torque. The scheme you can see in this slide shows the complete model using the torque estimation, and the comparison between the estimated torque and the measured one can be used for the input for some applications such as virtual force sensor or collision detection or preventive maintenance and so on. For the experiment, 2 robots on the same model, effort ER3A, were used for the experiment, and we named them Robot 1 and Robot 2. The data acquisition was repeated 4 times for each robot on different days. And to have comparable environment condition, all the tests were executed in the morning after at least 8 hours of robot rest, and with the same environment temperature of about 20 degrees. Both robots showed very similar behavior. The curves exhibit similar trend. The range of the curve value also were equivalent, and this confirmed the repetitiveness and the robustness of the method. Initial parameters should be independent of the temperature, and the numerical estimation will be expected to give a constant value. The result shows instead that they also had an asymptotic behavior. However, the range of the variation is generally minimal. Example of the result for the initial parameter represented here in this figure that clearly shows that the estimated value of the parameter changes with cycles, but the variation is very little. So it's confirmed that the identification procedure is robust and suggests that the initial parameter estimation can be performed after a short warming up period to avoid some mathematical error. The friction instead depends on temperature, which increases robot activity. Therefore, a time-dependent trend with an asymptotic behavior is expected for this parameter, as you can see in the depiction on the left. Because of these friction changes, the model mismatch is evident comparing 2 experiments, one executed at the robot startup and one after the thermal transient. As an example, the figure on the right shows the difference in torque obtained by moving the robot with the very same trajectory but a different thermal condition.
it is worth noting that how taking the temperature into account permit to have an excellent prediction of the working and both condition, hot and cold. So thank you very much for your attention. And if you have any questions.
Okay, thank you very much, Roberto, for your nice presentation. Now, I kindly ask Massimo and the panelists, the speakers, to turn on the cameras so that we can start the last part of our program, consisting of a round table and discussion on the papers. So you can also use the chat or raise your hand so we can moderate, myself and Massimo, we can moderate the discussion. Massimo, if you have any comment.
Yes, I think that we are all Italian people. Couldn't we speak Italian? Because there's no foreign people attending the session, I think. I don't know if it is, is it allowed or if we have to stick to the English language.
Yes, we can. I think that's fine. I think we can. Let's have a look at the participants, and if it is only Italians, I think we can have a chat in Italian. Yes.
We have an Italian-English participants in Perla Maiolina, but I think she would not be offended if you speak Italian.
Okay, if there is...
I can definitely speak Italian. Probably better than you.
Ok, allora parliamo in italiano per l'ultima parte del programma. Prima di tutto apriamo i lavori presentati a una sessione di question answer, cioè se avete delle domande specifiche da presentare le possiamo rivolgere al singolo speaker. Segnalo che abbiamo avuto un'eccellente distribuzione dei lavori con argomenti che veramente spaziano su ambiti molto ampi. Robotica industriale. Salve. Se volete intervenire vi chiedo di alzare la mano in modo da poter intervenire uno alla volta. Noi stiamo guardando, per cui se c'è una richiesta ripeto, faremo prima un giro, eventualmente ci fossero dei quesiti specifici sui paper, dopodiché potremo fare un attimo riassumere, tirare le somme dell'esperienza di oggi anche alla luce dell'ambito RIM. Dopodiché spenderemo anche due parole su quello che avevo accennato all'inizio, cioè la possibilità di avere anche uno special issue dedicato. Avevo segnalato due possibilità, uno è il Journal of Mechanics and Control, il JOMAC, Rotto e Bella, e l'altro è MDPI Machine Open Access. Essendo section editor in chief ho qualche gratuità, quindi se qualcuno diciamo solleva questo tipo di difficoltà possiamo appunto sentirci e valutare questa opzione. Direi che mi pare di non vedere mani alzate, non vi affollate prima di tutto. Se non vi fossero insomma domande di carattere specifico, magari seguendo un po' l'ordine degli speaker, chiederei di fare un intervento per risaltare un po' quelli che sono secondo voi i challenges, cioè i futuri obiettivi. Abbiamo visto oggi quali sono le sfide che ci poniamo per il prossimo. Quindi magari per semplificare le cose, Massimo, non so se sei d'accordo, potremmo seguire l'ordine degli speaker.
Io Giuseppe, se Se d'accordo vorrei aggiungere un'altra domanda, ovviamente chi magari, tanto che facciamo questa tavola rotonda, se qualcuno ha, diciamo, insomma, uno spunto da fornire su questo. Cioè, attualmente siamo in un momento in cui l'intelligenza artificiale, diciamo, è in voga, no? E sta raggiungendo dei risultati interessanti, e anche ovviamente, diciamo, in robotica è sempre più applicata. Machine learning, intelligenza artificiale, sistemi esperti. Quindi quello che qua siamo quasi tutti colleghi, diciamo, di meccanica applicata. Mi piacerebbe sentire il parere di qualcuno, diciamo, di noi, che ruolo può avere ancora, insomma, che ruolo può avere oggi, diciamo così, non dico la meccanica applicata, ma il nostro approccio, diciamo, che è basato, diciamo, sulla modellazione della meccanica, della dinamica, no? Di fronte a, insomma, reti neurali, machine learning. Quindi c'è ancora spazio per diciamo, una modellistica, oppure i nostri spazi sono ristretti? Questo, così, mi piacerebbe sentire un po' il parere dei colleghi, se qualcuno di loro ha un'opinione in merito.
Perfetto, come dicevo, magari seguiamo un po' l'ordine degli speaker, anche se dovesse appunto esserci qualche argomento da porre sul tavolo, assolutamente potete farvi promotori. I primi speaker siamo io e Massimo, su guarda caso. Direi di passare a Boschetti, Minto e Trevisani, se c'è un intervento da parte vostra. Vedo che si è unito Giovanni anche, magari se puoi aprire la telecamera, ci facciamo un saluto.
C'è anche Matteo, comunque, c'è anche Matteo Palpacelli, se vuole intervenire.
Io avendo un background molto simile a quello di Massimo, cioè, ho un po' di difficoltà a trovare queste connessioni con gli aspetti, insomma, di intelligenza artificiale. Noi, insomma, collaboriamo sulle parti, insomma, di modellazione nella robotica, anche in altri campi ovviamente, ma diciamo che l'aspetto un po' più di intelligenza ci sfugge un po'. Quindi chiederei a qualche altro collega che magari è un po' più esperto.
Di certo noi non siamo gli esperti di intelligenza artificiale, quindi spero ci sia spazio per continuare a lavorare sui nostri argomenti di modellazione.
Sì, ti sentiamo un po' disturbato.
Cinematica, dinamica di manipolatori. Aspetta, ho perso un attimo.
C'è un delay probabilmente, ti sentiamo un po' disturbato. Che adesso non ti sentiamo proprio. Ok.
Eccomi.
Eccoli. Benissimo, era forse la rete.
Sì, dicevo, spero per rispondere a Massimo che ci sia ancora spazio di continuare, altrimenti la meccanica applicata viene un po' schiacciata se lasciamo il tema all'intelligenza artificiale.
Benissimo.
Can I add something? Ah, scusate, in italiano.
Sì, vai.
Credo, nel mio campo di soft robotics, naturalmente la modellazione è più difficile, perché abbiamo sistemi che sono, in teoria, hanno infiniti gradi di libertà, e quindi è più difficile modellare questi sistemi. Per esempio, per il controllo, diciamo, per poter fare un controllo accurato di posizione, abbiamo necessità di modellare questi sistemi, e chiaramente sistemi basati su data driven, quindi modellare, imparare il modello, diciamo, tra l'attuazione e la posizione e la postura del robot, hanno sicuramente fornito dei vantaggi. Però c'è sempre il problema, dal mio punto di vista, della trustability di questi sistemi, e quindi avere un modello che ci può garantire, come dire, da un certo punto di vista, che stiamo facendo la cosa giusta, secondo me continua ad avere un valore. Quindi riuscire a magari integrare queste due realtà in futuro può essere qualcosa di importante, un po'. Cioè, quindi avere, come dire, un modello che ci permetta di avere una conferma che quello che abbiamo imparato usando data driven methods ancora, cioè, è valido, e Quindi io vedo anche una sorta di integrazione, ecco, nel futuro di questi due sistemi.
Perfetto, grazie per
Io
la...
posso aggiungere una cosa, nel senso, noi nel nostro gruppo lavoriamo molto con multibody in SimScape e ad esempio nelle ultime versioni del SimScape di MATLAB c'è proprio un'apertura ai corpi deformabili che prima non c'era, cioè abbiamo blocchetti già integrati in questo senso che MATLAB stesso sta sviluppando, quindi non so, magari se già li hai guardati, potrebbe essere uno spunto su questo che hai appena detto, sull'uso dell'aggiunta della deformabilità alla modellazione, che sicuramente è una challenge rispetto al corpo rigido.
Perfetto, grazie Chiara. Non so se
Simulatori? Abbiamo usato i simulatori, ma in genere sono i simulatori per noi, cioè a parte finita Element Simulation, se prendi simulatori per robots, in genere simulano sistemi lineari, mentre i sistemi soft per noi sono altamente non lineari, quindi non sempre riusciamo a... oltre al fatto che almeno simulatori, quelli che adesso esistono per robot rigidi, appunto sono in genere per robot rigidi, quindi abbiamo poi difficoltà a utilizzarli per software.
Magari puoi guardare se già in SimScape c'è un'apertura verso anche la software robotics, che sicuramente è una materia che va in sinergia anche con la scienza dei materiali.
Sì, esatto.
Diciamo, mi sembra uno dei rami della robotica che è altamente interdisciplinare, perché vedo una sinergia di reti neurali, di scienza dei materiali, di modellistica, di robotica, insomma c'è davvero un po' di tutto.
Assolutamente sì, grazie, guarderò.
Perfetto, non so se Massimo Solazzi, che ho qui nell'ordine della mia scaletta, vuole aggiungere qualcosa, vuole appunto porre qualche accento specifico su questo argomento. Non so se ci senti, se è sparito, ho perso in vista. Oppure in ogni caso, come dicevo, per moderare gli interventi, salvo richieste particolari, seguirei la scaletta. Quindi c'è anche Agostini, che ho il piacere di avere qui in presenza in aula. Non so se vuoi aggiungere qualcosa, vuoi venire qui a fianco a me o da lì, come vuoi. Io sono qui a disposizione. Intanto Massimo Solazzi lo vedo, ma forse non ci sente. Se hai qualcosa da aggiungere, sull'argomento che abbiamo introdotto di carattere generale, cioè il legame che si crea tra l'intelligenza artificiale, che sta guadagnando comunque un ruolo dominante o comunque in crescita in quello che è l'ambito meccatronico, c'è sicuramente una parte importante di meccanica, di simulazione, come diceva Massimo, ma sta guadagnando rilievo la science, tutto quello che c'è adesso.
Allora, io penso anche con l'esperienza del Collaborative Robots, quindi tutti i task che abbiamo eseguito anche noi nel nostro gruppo di ricerca per migliorare l'interazione, avere un'intelligenza artificiale che riesce a, diciamo, aiutare questo miglioramento e quindi che sia performante, sicuramente un aiuto. Però diciamo, l'attenzione, secondo me, da mia esperienza di ricercatore, va sicuramente molto data anche alla tecnologia dei materiali, quindi la parte di soft robotica e l'intelligenza dei materiali più che artificiale, nel senso che la parte di computing per elaborazioni di sensori, di dati ai sensori sicuramente è importante, ma diciamo quello che ho visto molto, insomma, sviluppata negli ultimi 20 anni molto di più con attenzione rispetto a quella dei materiali. E quindi secondo me adesso non bisogna tralasciare sicuramente un distacco tra queste due, devono andare insieme, però è importantissimo anche pensare che solo con l'intelligenza, diciamo, di materiali giusti e anche con la soft robotica, quindi pensare alle non linearità, iniziare a gestire, a computare, diciamo, con l'intelligenza artificiale i comportamenti non lineari, sicuramente la combinazione dei due disruptive, diciamo, in questo settore, ed è la strada giusta. Quindi devono andare di pari passo e non far aumentare il gap di ricerca.
Ottimo, condivido appieno la tua opinione e appunto è questo il nostro focus al momento, riuscire a mantenerci al passo con queste sfide. Vedo che Massimiliano ha alzato la mano, quindi cederei senz'altro la parola. Se puoi anche accendere la telecamera.
Sì, no, guarda, siccome ho problemi di connessione, quindi preferivo stare, anch'io vi ho oscurato perché ultimamente ora mi stava saltando di continuo, quindi limitavo al minimo, insomma, la banda, scusate. No, volevo aggiungere una cosa molto veloce, ora spero di non sovrappormi a quello che hanno detto le altre persone perché ho avuto appunto un po' di problemi a seguire, ma io volevo ricollegarmi proprio alla domanda che aveva fatto Massimo, no? Quindi, come si possono anche, come si può vedere le nostre tematiche di moderazione con l'intelligenza artificiale, vedendo, almeno per nostra esperienza, per cui non è che per forza, diciamo, il topic e le due approcci devono essere per forza in opposizione, antagonisti, oppure un'alternativa, o faccio una modellazione oppure utilizzo un'intelligenza artificiale. Cioè, quello che sicuramente sarebbe interessante, su cui sicuramente possiamo dare, diciamo, possiamo lasciare un'impronta, lasciare un segno, sarebbe proprio diciamo, modificare le tecniche di intelligenza artificiale applicandole sulla base di una modellazione che è propria del sistema fisico, quindi della meccanica applicata. Noi chiaramente abbiamo, per mia esperienza appunto per la determinazione di diciamo dei sistemi complessi abbiamo visto che insomma applicando prima, sulla base di chiaramente un modello meccanico, il caso era delle deformazioni di un oggetto del continuo, diciamo, quindi partendo dal modello meccanico, applicandoci poi un algoritmo che era un pochino più proprio per l'intelligenza artificiale del data analysis, abbiamo ottenuto ottimi risultati. Questo per dire che chiaramente non è che bisogna vedere le due approcci come, diciamo, due alternative, però sicuramente molte volte la simbiosi è possibile, e come molte volte se si riesce a far collaborare le due tecniche di solito si ottengono risultati migliori. E molte volte potrebbe essere appunto interessante. Molte volte chi si occupa di intelligenza artificiale, di esperto di intelligenza artificiale, non è abituato all'approccio, diciamo, modellistico, e quindi lì potremmo, diciamo, collaborare con loro, intervenire noi, e noi nel senso come gruppo, insomma, come persone che hanno le competenze, l'approccio con lo scopo appunto di evolvere le tecniche che ci sono ora.
Perfetto, grazie Massimiliano. Anche qui devo dire che è un pensiero abbastanza condiviso e condivisibile il tuo. Continuando su questa stessa linea, non so se ci sono altri interventi, in particolare nell'ordine credo ci siano i colleghi di Pavia, in particolare mi pare che Marco Carnevale volesse fare un breve intervento, non so se ci sente, vedo se ci sente ci può dare un feedback, aprire la telecamera.
Sì.
Tutti i colleghi di Pavia, non so qual è la vostra visione, il vostro punto di vista su questo tema che abbiamo sollevato.
Sì, posso dire, diciamo, come sapete, la nostra attività nell'ambito della robotica nasce in tempi relativamente recenti, quindi almeno come laboratorio di Pavia da qualche anno che ci siamo dedicati, noi da meccanici applicati, io e il collega Giberti, abbiamo iniziato ad approcciare il mondo della robotica, quindi abituati a progettare macchine, abbiamo sempre considerato la modellazione della meccanica. Qui a Pavia il contesto del Dipartimento di Ingegneria Industriale è molto incentrato anche sui temi dell'automazione e dell'intelligenza artificiale, quindi diciamo stiamo cercando di espandere l'attività in questa direzione. Questa premessa per dire che non sono al momento in grado di fare una valutazione di prospettiva sul ruolo della modellazione piuttosto che dell'intelligenza artificiale.
In ogni caso la vostra applicazione è quella che avete presentato.
Sì, diciamo lì si tratta di, non c'è una vera e propria intelligenza artificiale, sono tecniche di comunicazione, quindi semplicemente analisi del segnale cerebrale, quindi una sorta di analisi dati classica e trasferimento del comando alla macchina per switchare da una modalità, diciamo, di task autonomo a un task collaborativo. Quindi poi c'è un controllo aptico classico con sensore di forza che permette una movimentazione da parte dell'operatore. Quindi diciamo non c'è dietro un vero e proprio algoritmo di intelligenza artificiale, se non la gestione di segnali che provengono dal caschetto, con l'obiettivo, sempre diciamo rimanendo nel tema della robotica applicata, di provare a vedere se quei due soli sensori che abbiamo utilizzato nel Brain Computer Interface possano essere sensori poi implementabili, per esempio negli elmetti della sicurezza, quindi anche in un contesto industriale.
Perfetto, ti ringrazio per il tuo intervento. Non so se Chiara Cosenza o comunque Enzo Niola, non lo vedo, se volete aggiungere qualcosa sul filone del discorso attuale. Mi sembra che già Chiara fosse intervenuta in precedenza. Anche per Chiara.
Sicuramente
anche da condividere quello che può essere la visione per i prossimi 2 o 3 anni dell'orizzonte di ricerca in questo senso.
Io penso che l'integrazione dell'intelligenza artificiale nella meccanica sarà un percorso naturale, soprattutto perché molti di noi si stanno muovendo verso il veicolo autonomo come linea di ricerca. Quindi vuoi o non vuoi, diciamo, gli algoritmi più avanzati bisogna integrarli anche all'interno di un contesto di ricerca. Diciamo, io nel mio piccolo non ho ancora esperienza di questo, se non per la presentazione che ho fatto oggi per, diciamo, la Mechatronica, ma quando mi sono interessata dell'uso di sistemi di visione per il controllo, in qualche maniera abbiamo dovuto scrivere degli algoritmi, seppur semplici, che comprendessero l'ambiente per far muovere il sistema meccanico. Quindi un po' di intelligenza artificiale fatta in piccolo è necessaria per questo tipo di applicazioni.
Perfetto, grazie Chiara per questo ulteriore commento. Vedo che tra i partecipanti c'è anche Matteo Zoppi di Genova, non so se vuole aggiungere, intervenire a completare quello che è stato l'intervento di Perla Maglioni. Ti vedo tra i partecipanti, ma non sono sicuro tu mi possa sentire. Matteo, ci sei?
Guarda, credo che Matteo partecipi a pezzettini, ma ha detto che ha un'altra riunione in parallelo, quindi un po' partecipa, un po' no.
Perfetto, va bene, magari lo sentiamo appena potrà, se vorrà collegarsi, potrà collegarsi. Abbiamo ancora l'ultimo intervento, diciamo, iscritto nella lista, che è presente qui, quindi il collega di Brescia, Roberto Pagani, lo chiamo qui, se vuole aggiungere qualche commento.
Io essenzialmente, molti mi hanno tolto le parole di bocca, ne sono d'accordo con tutto quello che avete detto. Anche io, se fossi partito prima, diciamo, avrei ripetuto che secondo me i due approcci non devono assolutamente dividersi di troppo, ma devono, diciamo, crescere simultaneamente, almeno per il mio ambito, che sono all'ultimo anno di dottorato, fra pochissimo concludo e mi sono occupato, diciamo, di modellizzazione dinamica pura, quindi il mondo dell'intelligenza artificiale, machine learning, così, non l'ho approfondito molto, però sto iniziando a guardarmi intorno perché adesso dovrei continuare con un assegno di ricerca a Brescia e dovrei affrontare anche questi argomenti, e l'obiettivo è proprio quello di sfruttarli il più possibile per continuare comunque a, diciamo, toccare con mano, modellizzare effettivamente e avere l'approccio nei momenti, diciamo, più crisi, nelle parti dove c'è più difficoltà, come ad esempio mi viene in mente, ho fatto delle applicazioni di robotica collaborativa dove ho utilizzato degli algoritmi simili a questi qua innovativi su più sistemi di visione che sulla robotica, mantenendo il modello del robot e la dinamica, eccetera, per la movimentazione, mentre il sistema di visione, quindi erano due diciamo, percorsi diversi, che però alla fine venivano uniti sotto la stessa fascia. Quindi io spero vivamente che nei prossimi anni le due cose continuino a crescere contemporaneamente e non si crei divario. Io nel mio piccolo cercherò di muovermi in questo modo e spero che si continui così essenzialmente.
Perfetto, grazie Roberto per il tuo intervento. È chiaro, questo penso un po' tutti noi condividiamo un background comune e il nostro sentire è quello di, insomma, muoversi in questa direzione. Il trend è chiaro, ma al tempo stesso valorizzare quello che è il nostro background, le nostre competenze e imparare a integrarle un po' di più in quello che è un sistema che diventerà via via sempre più complesso. Massimo, vuoi aggiungere qualcosa?
No, solamente per dire che sì, la mia domanda era un po' provocatoria, nel senso che avevo già una mia opinione, che poi insomma è quella dei colleghi che hanno parlato, quindi non devo aggiungere niente di particolare. No, credo che soprattutto i più giovani, insomma, adesso lasciami fare questo intervento, non potranno fare a meno dell'intelligenza artificiale, quindi credo che questa sia una strada obbligata, ma non perché siamo costretti, perché obiettivamente è uno strumento importante che ci darà molte opportunità, però senza abbandonare il nostro approccio. Ritengo che veramente anche la realizzazione di un modello, se anche sia cognitivo, possa essere fatto in modo efficace basandosi, diciamo, su un modello, diciamo così, meccanico. Quindi fittare dei dati, diciamo, può essere fatto anche con data analytics e altro, diciamo, su un modello magari semplice meccanico che guidi, diciamo, questo algoritmo di fitting. Quindi comunque, ecco, non ho detto niente di nuovo, ma sono contento di sentire dai colleghi, diciamo, che abbiamo questa visione comune, almeno noi, diciamo, che siamo qua oggi, su quello un po' che è, diciamo, il rapporto tra la meccatronica, lato meccanico e l'intelligenza artificiale, perché credo che, a parte dove siamo ospitati oggi, insomma, no, questo evento organizzato dai RIM, anche i futuri progetti, diciamo, di Horizon Europe, eccetera, ci guideranno verso un'integrazione stretta tra la nostra disciplina e l'intelligenza artificiale. Quindi mi sembra che siamo tutti pronti e, insomma, abbiamo tutti l'intenzione di percorrere questa strada, mi fa piacere. Quindi io concludo così il mio intervento.
Perfetto, aggiungo solo un ultimo commento agganciandomi a quello che hai detto tu. Chiaramente questa iniziativa di oggi, questo workshop, è organizzato in seno all'IRIM, che appunto per sua natura ha uno spirito multidisciplinare, e questo un po' la dice lunga, insomma, non possiamo più fare a meno di confrontarci con i nostri vicini di casa, questa almeno è la mia opinione. Riguardo a questo vi ricordo che il workshop di oggi è stato organizzato nell'ambito di un working group di IRIM che si chiama Intelligent Mechatronics, che ho avviato da qualche mese. Ci saranno, sono in corso di attivazione vari altri working group. Qualcuno di voi è stato già invitato, ma l'invito è esteso a tutti. Quindi se qualcuno è interessato alla disponibilità, c'è la possibilità di partecipare ai vari working group. Se qualcuno non è al corrente, non ha avuto occasione in precedenza, Domani pomeriggio c'è uno dei workshop e diciamo illustrerà un po' queste attività dei working group, quindi è sempre gratuita la partecipazione. Se volete, domani pomeriggio credo che sia il working group e il workshop 8 organizzato da Pascucci e Oddo. Quindi se volete partecipare e se volete insomma segnalare una vostra disponibilità, un vostro interesse, lo potete fare a me o anche direttamente appunto tramite i coordinatori dei working group, i promotori dei working group, che sono proprio Pascucci e Oddo. Vi chiedo se avete qualche altro punto da sollevare o qualche altro argomento da trattare, altrimenti direi che praticamente on time possiamo tra 2 minuti salutarci e chiudere l'evento.
Beh, Giuseppe, tu avevi accennato con la possibilità, diciamo, di raccogliere qualche contributo su quelle riviste, cioè operativamente come conti di fare, insomma, manderai un invito, non so se...
Sì, l'idea sarebbe la seguente, se la condividete. Io manderò una mail a tutti i partecipanti dell'evento di oggi chiedendovi se siete interessati, non c'è nessun tipo ovviamente di forzatura. Se raccogliamo 4 o 5 adesioni, almeno 4 o 5 adesioni, possiamo puntare a avere un special issue dedicato, altrimenti possiamo organizzarci anche, diciamo, inserendoci sugli special issue già attivi. Quindi, ripeto, se sei d'accordo anche tu Massimo, partirei da un'email a tutti i partecipanti, dopodiché diciamo, dopo una vostra manifestazione di interesse valuteremo poter esprimere nel migliore dei modi questa opportunità. Che cosa ne pensate? Massimo, sei d'accordo? Non ti pare?
Sì, personalmente sì.
C'è qualcuno che ha già un'idea di se questa iniziativa può essergli di interesse? Magari ci dovete pensare un pochino. Che dici Giovanni?
Ah, beh, al momento penso che possa essere interessante, insomma, per più di qualcuno. Poi
benissimo.
Magari valutiamo un attimino le tempistiche, ci puoi dare.
Siamo pure stanchi a quest'ora, per cui tranquilli, via mail lo gestiamo.
Perfetto, benissimo.
Sempre un piacere, ovviamente, se riusciamo anche a trovare delle sinergie, delle ulteriori opportunità di collaborazione tra noi, che condividiamo bene o male gli stessi interessi. C'è ampio spazio per fare ancora di più. Benissimo, sono le 17:30, quindi esattamente come da programma. Io vi do un caloroso saluto da Roma e spero di vedervi di persona, di vederci di persona il più presto possibile, perché è veramente passato tanto tempo. Quindi,
grazie.
Ciao, arrivederci.
Ciao, a presto.
Ciao a tutti allora.
Ciao.
A tutti.
Ciao.
Ciao a tutti.
Arrivederci a tutti.
Grazie a tutti. Arrivederci.